Hi, this is the 7.2 intro video for AP Calculus AB. We're going to be looking at the disk and washer methods to find volume, and then later on we'll also be looking at what we call volume by cross sections. That'll come at the end. This video is about the disk method. The disk method is a way to find the volume of what we call a solid of revolution. A solid of revolution is a three-dimensional shape formed when the graph of a function is revolved or rotated around an axis. So I want to give you some visual on this. I got a couple of, I think some good visuals for you. So we're going to take a function and I'm going to graph it. We're going to call it, this is maybe be something like y equals square root of x. I have a good demonstration for you here in just a second with this. Let's say that we cut this y equals root x function off right there, and it creates this little region right in here. And in the past, earlier this year we found the area of that region. We're going to do something a little bit different with it this time. I want you to imagine for a second, what if we took that region and we revolved it around the x-axis? So we took this whole gray region, revolved around the x-axis. It could look something like this. Where down here we'd have this reflection of that curvy top part. And there would be, all these circular elements to it. Something like this. You could see that it would look maybe, I don't know, like a bullet or something. It'd be a solid shape. And that rotation around the x-axis is what's causing the solid, the three-dimensional shape to form. When I see in class, when we're working on this, we're actually going to break out some Play-Doh and try to make shapes like this, and some of them get sort of complicated, and we'll try to do our best to visualize those. So I've got a little demonstration that I want to show you here in just a second. But let's talk real briefly why this is called the disk method. I'll switch screens on you here in just a second. We'll look at why it's called the disk method, and then I'll show you the little demo I think will be helpful for you in visualizing this. So what I'm going to do is I'm going to redraw that graph from before, y equals root x. Something like that. We're going to cut it off here like we did before. Here's the gray region again. And to help us visualize this, we're going to use a disk and a representative rectangle. So what I'm going to do is draw in a representative rectangle right somewhere here in the middle. It's going to stretch all the way down there to the, let me try that again. I want it to go all the way to the x-axis. There we go. Something like that. And what I'm going to do is I'm going to imagine that representative rectangle being rotated around the x-axis. So I'll do my best to draw a visual here. If I did that, it would look something like this. And of course it would go back into the page and so on and so forth. And you can see, it forms a disk. So like the word disk, it's like a CD or a DVD or something like that. Of course it's tipped up on its end. You could also think of a disk as a cylinder. This will be important here in a second when we look at the formulas here. And of course what I would be doing is let's try that again. I would just be doing lots of these little disks in order to create this whole shape. So I'd have bigger ones out here at the end, and it would just create this larger and larger three-dimensional solid shape we could find the volume of. So I want to do a little demonstration here. Actually, I want to say this first. For the disk method, and really for all the methods that we'll use, that representative rectangle will always be perpendicular. That's really important to the axis of rotation. So if we're rotating around an x-axis, that representative rectangle, like I drew earlier, would be vertical. If we happen to be revolving around a y-axis, then the representative rectangle would be horizontal. So that's quite important. That'll set up everything that we do with these. But for the moment, I want to show you a little demonstration with a similar function to this, hopefully a little better illustration than my drawings. So this is a Wolfram Alpha demonstration that you guys could download on your own computers if you wanted to. I just want to point out the function that we are working with is over here on the left. my mouse isn't really showing up here. You see the function is root x. It's the one we were just working on. And what I'm going to do, down here a little bit lower, it says number of segments. And I'm going to take the slider and I am going to increase the number of segments. Right now there's just 2 segments, but as I increase the number of segments to 9, you can see all these disks that are being formed with this solid of revolution. So I can kind of twist this a little bit and you can kind of see that it's that bullet shape that's going on there. There's the back end of it. I can rotate it a lot. I can rotate it all through here. But if you notice, it's that function y equals root x that is essentially telling the disks how big they need to be. I can take the number of disks much higher. And I'm sure you can imagine that the more disks I have, the skinnier they are, and the better the calculation here. I'm up to 28 disks. This is looking, really like a really solid shape now. Let me get this. Oh, I want it. There we go. And then, of course, you can, push it up there. How high does it go? 30 disks, right? You can still see that there's a bunch of disks in there. The thought being that if I take the number of disks and make the number of disks approach infinity, then the width of each disk would then be approaching 0, and we would have a perfect volume of this particular shape. So this, of course, applies to more graphs than just y equals root x. This one gives us some flexibility, get some different shapes here. So this is a parabola. So as I take this, we can see the parabola right there curving up there. If I take the number of segments and increase it a little bit, we get a shape like this. Some of them can get pretty crazy. And then a sine graph over a certain domain there. This can look, I guess I don't know how to describe that exactly, maybe an onion, something like that. And then we could have cosine, depending on the domain. This can look pretty interesting, obviously. Looks like an hourglass, I guess. Well, of course, all this is based simply on rotation of a representative rectangle that creates a disk, and then if you add up the number of disks over the course of an interval, then you end up with a solid shape like this. I hope that's a good demonstration. There's more. One of the demonstrations we'll do in class, like I mentioned, is just to use Play-Doh and try to make stuff like this. I think it's a good way to try to understand what's actually happening and the shapes that result. Okay, so we're going to go back to our regular notes here and talk a little bit about the formulas, and then we'll be done. So the formulas to find the volume of one of these solids of revolution are actually pretty simple. If we can just remember that volume equals pi r squared, we'll be in a pretty good spot. So if you've got a horizontal axis of revolution, like the x-axis, then everything is going to be in terms of x, and you would have a volume formula of pi times the integral from a to b of r of x squared. For a vertical, it would be the exact same thing, except everything would be in terms of y. So this would be like if your axis of rotation was the y-axis. Pi, we all know what pi is. Let's talk about what the r's and the the dx's and all that are. In order to do this, I'm going to draw one of those disks that we were just looking at in the little demo and like I drew earlier. And then I'm going to draw a little center of the disk through this shape, something like that. This would be like the axis of rotation. Hopefully you can see the three-dimensionality of that. Hopefully that's a good enough drawing for you. If not, I'm sorry. I'll do my best. So what I would want you guys to think about here is that r of x, we could think of this as the distance, there we go, distance from the axis of rotation to the outer edge of the region. Or you could just think of it as the radius, right? If you think about that disk, the distance from the axis of rotation would be from here, right in the center, out there to the outer edge. That could be thought of as a radius, right? And of course, r of y is the same thing. I'll just put distance from axis to outer edge. There we go. Okay, and then dx is going to be the thickness. or dy. It's going to be the thickness of, let's try that again, thickness of the disk same thing with dy. So I hope this makes sense when we think about why the volume formula is what it is. I want to finish with this. Hopefully this will make sense to you. Remember, a disk is simply a cylinder. So I'm going to take this disk and I'm going to draw it in the way that we typically see cylinders. And I want you to think about the volume formula for a cylinder. Maybe from geometry you remember this, maybe you don't, but the volume formula for a cylinder is pi r squared times height. So if you think about how this works, the radius is probably what you're thinking it is. It's the distance from the center out there to the outer edge. So you can see that that's really the same. And then the height would be right here. And the height for us is represented with a dx because we want flexibility for that thickness to approach 0 as we try to fill this solid with very skinny disks. And so pi r squared h, when you think about that, when we compare it to pi r squared dx, it really is the same thing. We just have to put the integral in there so that we can cause the disks to be approaching a thickness of 0 and therefore have an infinite number of them, and therefore find the exact volume of the shape. Your big takeaway here is we've got to have these formulas solid. I wanted to show you where they come from. So you have an understanding of it, and maybe if you do forget the formula, you might be able to kind of reason your way back towards it. So when you come to class next time, make sure you have all this down solid, and we will try to work with the disk method to calculate some volumes and create some interesting shapes with Play-Doh, and hopefully have a lot of fun with it. So see you next time in class.